This presentation is all about intermolecular forces, which is really big in determining the physical properties of substances. So this is going to be really integral for all of organic chemistry for us.
So we have two kinds of compounds, ionic compounds and covalent compounds, and both of them have their own different kinds of intermolecular forces. Intermolecular forces are really important because they help to determine the physical properties of any substance: melting points, boiling points, surface tension, solubility. And for us, what's going to be important is their melting and boiling points and solubility. That's what we will talk about for organic compounds. And you have to know this for all the functional groups. That's why it becomes really important. Okay. So ionic compounds inherently have a very strong intermolecular force because the force between their ions is called electrostatic force, and it's one of the strongest forces because it's between a positive and a negative. And if you look at the melting points of ionic compounds, it's very high. And so ionic compounds inherently polar and very high intermolecular forces. Covalent compounds, on the other hand, are a little bit different. There are three different kinds of intermolecular forces in this: dispersion forces, dipole-dipole forces, and hydrogen bonding. Now remember, when we talk about intermolecular forces, these are the forces between two different molecules, okay, or two molecules, separate molecules, not within the molecule. So when we learn about polar covalent bond, that is the polar covalent bond within a molecule, but intermolecular forces between two molecules may be the same, may be different. So the stronger the intermolecular forces, the higher the melting point will be and the boiling point. And the molecules which have the same kind of IM force or intermolecular force, they will dissolve in each other. Remember, like dissolves like. Okay, and so we'll be talking about all of these forces. So let's talk about the first intermolecular force, which is dispersion force. This is also called van der Waals forces, also called London forces. All of these are the same things. It is the force between internal electron distribution in any kind of a molecule, okay, which causes an induced dipole. So if you look at the bottom structure over here, here if you have a normal atom, these atoms can then give an unsymmetric distribution, okay, over here where the nucleus is on one side and the electrons are on one side, which means that the atom has a delta negative and delta positive all by itself. And this usually happens because of the size of the atom, okay, and I'll give you an example in a minute, but this is kind of what happens. And so when you have two molecules which are kind of like this, which have an internal distribution of electrons and protons on one side, when they come across another one, then the partial negative and the partial positive of the other atoms, they kind of start interacting. So this interaction, this is called induced dipole because the bond itself inside may not be that polar, okay, but because of the sheer size of the atom, this atom might end up showing an asymmetric distribution. This is best shown in fluorine, chlorine, bromine, and iodine. Okay, these are the halogens in this group number 7. Going down a group where fluorine is the smallest atom, chlorine getting larger, and iodine is the largest one. So if you look at the boiling point of all of these halogens, fluorine is the lowest and iodine is the highest, which means that fluorine, chlorine are gases, negative boiling points. Bromine is a liquid, and then iodine is a solid, okay, and that shows that the intermolecular forces in iodine are way more than bromine and definitely way more than fluorine or chlorine. So it means that there must be something that's working for it, and what is working for it is really this asymmetric distribution of what we call induced dipole. So iodine, being such a huge atom, can cause this internal distribution of electrons and protons, which then has this induced dipole type of intermolecular force. Then dispersion forces in straight chain versus compact molecule. That was the first one that we did, was the size of the atom, in which you had a small versus big size. Now we're going to look at when you have a straight chain compound versus something that is completely branched, okay? And when you have a straight chain compound, you have more surface area, a larger surface area, and because of the larger surface area, the interaction between two molecules can be a lot more. And because of that, the boiling points are usually high, okay, for these molecules. You can have the same kind of compound, but if it is branched, not a straight chain, now the surface area is not so much, and therefore the boiling point actually goes down, okay, for this one, because the intermolecular forces or attraction is not that much, okay. So the higher the surface area, the more the intermolecular force. Again, the forces here are still dispersion forces because the CH bond is not that polar, okay. So the only thing that's affecting the intermolecular force is dispersion force. In this slide, we're going to talk about the dipole-dipole moment. And the dipole-dipole moment is a fairly good intermolecular force. Okay, now in this case, in case of dipole-dipole moment, a molecule will have to show a dipole interaction, which means that it should actually have a dipole moment. Okay, so here are some molecules which show that. If you have a molecule like hydrogen or chlorine, which are homotopic, which means same atom, then there is no electronegativity difference. And if there is no electronegativity difference, then the dipole moment is zero. And remember that it's not just that these are homotopic, it's also that they are linear structures, okay? Because the dipole moment depends not only on what kind of atoms you have, but also in the shape of the molecule. All right, so we've gone through all of that before, so you should be able to predict all of this. And this table over here kind of shows you a little bit about the different dipole moments of molecules. So hydrogen, chlorine, 0 and 0. HF, definitely a high one because fluorine is highly electronegative and therefore the HF bond is extremely polar, and because of that this molecule shows a dipole moment. HCl little bit less, HBr less, and then HI is extremely less because the electronegativity is very low for HI. BF3, CO2, carbon dioxide and boron trifluoride, both of them are zeros because they have a symmetric structure, even though they have polar bonds. Remember, we talked about this. So they have a polar bond, but the dipole moment is zero just because of the shape of the molecule. BF3 is trigonal planar and carbon dioxide is linear. Okay, because of that, no dipole moment. CH4 is the same way, tetrahedral, but because all four atoms are the same, also because hydrogen-carbon bond is not that polar, dipole moment is zero. But look at CCl4, where all the four atoms are chlorine, again, no dipole moment. All right. On the other hand, if you substitute one of the hydrogens with chlorine one by one, then you start having dipole moment over here. Okay. And then we have NH3 and F3H2O. All of these molecules, they are not symmetrical molecules. Their shape will show that they are trigonal pyramidal or bent structures. And because of that, they will show a dipole moment. Remember, nitrogen has a lone pair of electrons, oxygen has two lone pair of electrons, whereas BF3 did not have any. So BF3 was trigonal planar, whereas NH3, ammonia, and nitrogen trifluoride, these are both trigonal pyramidal. Okay, and because of that, they have a dipole moment. And because of this dipole moment, their boiling points will be higher. Okay, so CH4 will be a gas, whereas these chlorinated methanes, they will be liquids, okay, because of the fact that they actually have a dipole moment. So here are some more examples of different molecules. So propane, which is only carbon, and hydrogen. That's it. No real difference in electronegativity, which means no polar bonds here. The dipole moment is very less, boiling point is very low. All of these different compounds over here, they have different functional groups. They have different heteroatoms. Okay, anything other than carbon or hydrogen, heteroatom. So oxygen, chlorine, and then oxygen here, and then nitrogen over here. So it gives you a good example of how different atoms and different shapes will affect the dipole moment and the boiling point. So CH3O, CH3, this is an ether. Ether, pretend this is like water, okay, which means in the shape is like water, except in water you have hydrogen, whereas in CH3 you don't really have the hydrogens connected to the oxygen. So the shape of this one is bent, and because this is bent, it does have a little bit of a dipole moment because oxygen is very electronegative. Okay, so you can see the change in the boiling point, okay, for this compound. Then when you get to methyl chloride, there is quite a bit of dipole moment and boiling point goes higher. Okay. Acetaldehyde, which has a carbon double bond oxygen, and this one is a trigonal planar structure, really high dipole moment. Okay, carbon double bond oxygen is a nice polar bond. Okay, and so now the boiling point is in positives. Okay, and then the acetonitrile, which is C triple bond nitrogen. Again, nitrogen is very electronegative, so really high dipole moment, a high boiling point. Okay, so that's how dipole moments will affect boiling points, which just means that the more dipole moment you have, the more intermolecular forces you have, and vice versa. So you really have to know the shapes of molecules. You have to know the electronegativity in order to understand the dipole-dipole moment. The last intermolecular force that we have to talk about is hydrogen bonding. This is quite a strong intermolecular bond. It's almost as strong as a covalent bond. Hydrogen bonding exists between hydrogen atoms that are bonded to fluorine, oxygen, and nitrogen, which, if you look at the periodic table, are very electronegative atoms. Okay, so the thing about the key thing here is that the hydrogen atom should be bonded to these three atoms, and it will show the hydrogen bonding with a similar kind of electronegative atom, which usually is fluorine, oxygen, or nitrogen. In rare cases, it will show it with something else, all right, or with some other atom, but usually you have to have fluorine, oxygen, or nitrogen connected to the hydrogen to show the hydrogen bonding. So here is an example, okay, and this one is for water molecules. The hydrogen bond is shown right here between oxygen and hydrogen. So here, look, oxygen is connected to the hydrogen. Oxygen is highly electronegative, so gives this bond a high polarity, and because of that, this is delta positive and oxygen is delta negative. So when two molecules of water interact, this delta positive and negative will attract each other, okay, and form a strong hydrogen bond. It's a very strong bond, okay. It kind of holds everything together like proteins and DNA and all that. So it's a very strong bond. So this is between water molecules where you have oxygen and hydrogen. This one here, the second one, shows the hydrogen bond between nitrogen and hydrogen. Okay, so this is not the hydrogen bond. This one, the dotted line, is the hydrogen bond. You can also have hydrogen bond between an NH and OH. Okay, because again, the hydrogen should be bonded to nitrogen and oxygen or fluorine. Okay, that's the important part. So between ammonia and water, also you can see hydrogen bonding. All right, so these two are going to be the most common ones. You probably will not see fluorine that much. Fluorine is a very unusual atom, very small, very tiny, very reactive. So you probably won't see so much of fluorine, but you will definitely see nitrogen and oxygen a lot in organic and then also in biochemistry. So comparison of IM forces, intermolecular forces, again H bonding, most strong, the strongest intermolecular force, dipole-dipole, and then dispersion force. The way things work is that almost every molecule is going to show some sort of dispersion force because each molecule is going to have electron density. So you will have dispersion forces for all of them. But the thing is that when you answer these questions and I ask you what is the major force involved, you have to select either H bonding or dipole-dipole or dispersion, not all three of them. You can't have H bonding in all of them anyway. Hydrogen bonding is exhibited only by certain types of molecules. Dipole-dipole, however, can be overlapped with hydrogen bonding because essentially the HO bond or the nitrogen-hydrogen bond, they actually exhibit dipole moment. But still you have to be very careful in selecting which one. Okay, you can't select all three of them, and a molecule that shows hydrogen bonding should not be labeled as a dipole-dipole interaction. Okay, so you have to be careful when you answer these questions. And again, dispersion forces are exhibited by all molecules, but you cannot use that as an answer for everything. Okay, so be careful. All right, so here we have an example. okay, of a molecule, and what kind of intermolecular forces are being showed here. So the CCl bond, that will actually show a dipole-dipole force, and the OH bond here, this will show a hydrogen bonding. Now the dipole-dipole force is also shown by the CO bond over here, the carbon double bonded oxygen. This also shows a dipole-dipole. So really this shows two dipole-dipole and one hydrogen bonding. Regarding the dispersion, yes, it will show dispersion, but that is not the most prominent bond here, okay? The most prominent intermolecular force is actually the hydrogen bonding, followed by the dipole-dipole. Here are some more examples. So if we have CHCl3, what kind of intermolecular force will you see? So in this case, you will see dispersion force as well as dipole-dipole, okay? Because the three chlorines in here give a dipole moment to this. But the important force here is dispersion force, because chlorine is a huge atom. Bromine, no doubt. Dispersion force, because there's no polarity, there's nothing else, there's no dipole moment. So this is completely a dispersion force. Calcium nitrate, electrostatic force. Why? Because this is ionic. CH3OH, the major force here is going to be hydrogen bonding, because you can see the OH, okay, quite clearly. So looking at these molecules, the second question, which one has the highest dispersion forces? This is quite simple. All you need to do is look at all of these molecules and see which one has the highest molecular weight. Okay, it doesn't tell you anything about the structure of the molecule. It just tells you about how many carbons and hydrogens there are. So that's all you have to choose. Now, if you were being asked about branching and straight chain, then the structure has been shown to you. Okay, but in this case, you just worried about the molecular formula. Okay, so this is the highest one that has the highest dispersion force, that is. Finally then, here are your keywords for this chapter. You need to understand the different electrostatic force, dispersion force, dipole-dipole, hydrogen bonding, and specifically how all of these will affect solubility, melting points, and boiling points. All right. So this table here is a little bit of an example of the different kind of forces we have, their strength, what kind you will see, and then of course some examples. Okay, so go through that and then let me know if you have any questions in class.